Unlock the secrets of GPT's tokenization algorithm. Let's explore byte pair encoding.
Imagine a world where every word needs its own unique ID. That's a massive vocabulary. Models like GPT need efficient ways to handle text. Byte Pair Encoding, or BP, offers a clever solution. BP learns to represent text using subword units, balancing vocabulary size, and handling unknown words effectively. We'll explore how BP achieves this. Let's consider the sentence. This is a test sentence. Initially, our vocabulary consists of individual characters. T, H, I, S, E, N, C, T. BP starts by counting the frequency of each character pair. The most frequent pair might be is. BP merges I and S to create a new token, is. Our vocabulary now includes is, reducing the need to represent it as two separate characters. After merging is, another frequent pair might be TH. BP merges T and H to form TH. Now our vocabulary includes TH, is, and the remaining individual characters. The sentence, this is a test sentence, can now be represented using these new tokens. This iterative merging process continues until a predefined vocabulary size is reached. For example, GPT-2 uses a vocabulary size of 50,257 tokens. BP's ability to create subword units is crucial for handling rare or unknown words. Instead of representing unseen word as a sequence of unknown tokens, BP might break it down into known subwords like un, seen, and word. This allows the model to understand and process words it hasn't encountered during training. The UNK token is still used for completely unseen characters. Per request it's tiny, but at scale, across millions of prompts, token inefficiency becomes real money. Building on BP's merging strategy, let's examine how it handles unseen words. Subword tokenization allows BP to represent words not initially in vocabulary. For example, unseen word can be split into unseen word. This is crucial for open vocabulary models. The model can still understand and process the new word based on learned subword representations. Now let's consider word piece, employed by BERT, which enhances BP. Unlike BP's frequency-based merging, word piece merges pairs based on likelihood. Word piece calculates the likelihood of different merges and selects the one maximizing the language model's likelihood. This helps in creating more semantically meaningful subword units. This difference can impact model performance. Let's illustrate with running versus ran. BP might merge R and U if frequent. Word piece analyzes context, potentially keeping running whole if likelihood is higher. For example, consider the sentence, the runner is running. Word piece might keep running as one token. Example values for demonstration. This nuanced approach enhances contextual understanding. Special tokens also play a vital role. Tokens like CLS, SEP, PAD, and UNK serve specific purposes. CLS is used for classification tasks. SEP, separate sentences. PAD sequences to a uniform length. UNK represents unknown tokens. These special tokens guide the model's understanding of input structure. Without them, model performance degrades. GPT-3 utilizes special tokens extensively. Now that we've covered special tokens, let's delve into token efficiency. It's measured by useful tokens divided by the total tokens. High efficiency reduces cost. Per request it's tiny, but at scale, across millions of prompts, token inefficiency becomes real money. BP might tokenize running as run and ning, costing 2 tokens. Word piece, calculating likelihood, might keep running as 1 token. BERT favors this. A 100K vocabulary often leads to higher token efficiency than a smaller 30K vocabulary. Multilingual models pose unique challenges. A 30K vocabulary might suffice for English, but not for Chinese or Arabic. Larger vocabularies like 100K plus accommodate diverse scripts. However, this increases memory usage. Normalization also plays a critical role. This involves lowercasing, Unicode handling, and accent removal. Imagine cafe versus cafe. Proper normalization ensures consistent tokenization. Hugging Face Tokenizers offers tools to normalize and tokenize efficiently. Building on the normalization process, let's explore real-world examples. GPT-3 uses a 50,257 token vocabulary with byte pair encoding. This offers a balance between granularity and memory footprint. Consider the phrase, tokenization is key. GPT-3 tokenizes this into 4 tokens. Tokenization is key. Each token corresponds to a numerical ID in the vocabulary. Example IDs are 464, 2068, 7586, 21831. BERT, on the other hand, employs WordPiece with a 30,522 token vocabulary. The same phrase, tokenization is key, becomes 7 tokens. BERT's tokenization yields, token, hashtag ISA, hashtag tie-in, is key, SEP. The key difference lies in subword tokenization. BERT splits tokenization into token, hashtag ISA, hashtag tie-in. This impacts token efficiency. Per request it's tiny, but at scale, across millions of prompts, token inefficiency becomes real money. Building on the BP and WordPiece algorithms, let's examine the practical implications of vocabulary size on model performance and cost. Smaller vocabularies like BERT's 30K offer memory efficiency. Assuming 1,024 dimensional embeddings, this translates to approximately 128 megabytes. Larger vocabularies, such as 50K used by GPT-3, consume around 200 megabytes. The trade-off becomes apparent when considering multilingual datasets. Conversely, a larger vocabulary often leads to fewer tokens for the same text. Consider the sentence, tokenization is key. With a smaller vocabulary, it might be tokenized into 5 or 6 tokens. However, a larger vocabulary might represent it with just 3 or 4. This token efficiency directly impacts API costs. GPT-4's pricing model charges per token, and fewer tokens translate to lower costs. Choosing the right vocabulary size depends heavily on your specific use case. For English-only applications with limited resources, a 30,000 to 50,000 vocabulary is often sufficient. However, for multilingual applications or specialized domains like code, a larger vocabulary of 100,000 or more may be necessary to adequately represent the diverse character sets and specialized terms. In summary, byte pair encoding, WordPiece, and vocabulary size are crucial elements in the tokenization process. Balancing memory usage, token efficiency, and language coverage is key to optimizing model performance and minimizing costs. While we've covered the core algorithm and trade-offs, the hidden complexity lies in handling rare words and out-of-vocabulary tokens.
Like, share, and subscribe to my channel for more AI insights. I'm the Code Architect. See you soon.